Right, so I'm going to say hello, and this is going to be a lesson on electrolytic cells. And hi Amy. So what we're going to look at is, whoops, let me get rid of that. We're doing this as the last lesson of the series for 3070 series for the 91393 standard. If you've got any questions, Amy, you're welcome to type them into the chat box, and I can, do my best to answer them. So let's have a look. What we're going to look at is look at electrolytic cells and then do a comparison with what we looked at last week with the electrochemical cells, galvanic cells, and we'll look at a few uses. So this is the electrolytic cell. Now, Amy, have you looked at or did you watch the lesson or join the lesson last week? No, you didn't. That's fine. I just wanted to see how many questions I could ask. I hope Andrew gets back, because he was here and then got knocked out when I recorded the lesson. So what we're looking at here is where we use chemical energy. And unlike the last time where chemical energy made electrical energy, we now have to have a power supply, so to produce a chemical reaction. So it's the opposite. Now I'm going to see if I can write on here. Yep, okay, that's great. Oh no, actually I can't even write on here. But what we're looking at, the same of what we looked at last time, cations to cathodes. So when we're looking at what goes where in this reaction, any cations will move to the cathode. I don't know if you can see, this is called the cathode. And a way to remember is cations to cathode. There are other ways to remember. The reduction happens at the cathode, so the C in reduction makes you think of C for cathode. Now the cathode is just this metal rod. In this case it happens to be copper for the one we've given here. So this metal rod here, it's where electricity can get through from the power supply into the rod, and those electrons then get handed over to the cations that arrive. So what I'm trying to show you here, this is the cation. It comes to the rod, it picks up electrons, 2 electrons, and it forms copper metal. So if it's gaining electrons, what type of reaction is happening? Oxidation or reduction? So Amy, if you'd like to type in, or if you don't know, just say don't know. It doesn't matter. Reduction. Great. And what's happening at the other, because these electrons have to come from somewhere, so the electrons are supplied by the zinc. So the zinc metal is giving up 2 electrons, which are going then up there to complete the circuit, and the zinc ions are going into the solution. So the zinc is moving out. So if we had zinc, sorry, I see this is a zinc solution. I got confused with the copper. The zinc is coming along here, picking up electrons, and is plating as a gray onto our copper rod that we've got here. Sorry, I did say the copper being deposited on there, but it's actually the zinc being deposited on there. So what's different is we have an electrical supply, but what's the same is, as a previous one, is the cations go to the cathode, and the reduction happens at the cathode. Oxidation happens at the anode, and the way to remember that is oxidation. The A is for anode. Another way is to remember it is the red cat, reduction at cathode, and anox, the oxidation happens at the anode. Now, if either of you have done physics before, you'll know that the short little bit there in this diagram is the negative, and the long line is the positive. Have any of you done that, say, in previous, in science level 1 or so on, when you drew cell circuits for electricity? Do you remember those batteries, right? One way to remember which is which is if you think of the positive end and the negative end. So if you think of the positive, it's made up of two lines. If we took the two lines and we put them together, it makes a long line. So the positive makes a long line, and the negative end makes a short line. So if you get given a cell diagram or a diagram of a battery, then that is one way to remember what is negative and what is positive. So the positive end of a battery, this is actually a cell because it's only got one cathode and one anode in it, but we tend to call it a battery just in the English language. So the long line is the positive end, the short line is the negative end. Any questions on the layout of an electrochemical cell? Nope? Okay, so the important thing is there are still the two rods, the two electrodes, like we saw last week. We still have the reduction happening at the cathode and the oxidation happening at the anode, but we have an electrical supply. What else is different? Because I see there's some more people here, and did anybody attend last week's lesson or watched a recording of it, or even have completed 3072? Okay, Michael, now I know you weren't too sure, but what is different to this cell to the last cell? Is there anything else you notice that is different? The one thing is different is we've got, instead of a voltmeter, we've got a battery, the salt bridge. So there's, I'll get to those that I'm showing there now. There's no salt bridge. So remember we divided the two reactions. We kept the oxidation separate to the reduction in the electrochemical or galvanic cell. We don't have to do that with an electrolytic cell. The other difference is in an electrochemical or galvanic cell that we did last week, we had a positive cathode. Remember that red cat with crosses for the eyes, and the anode was negative. Now, can you see there's an opposite over here? The cathode is negative, so this is the one thing you do have to remember. The cathode is negative. Now, if you think of why it would be, okay, it has to be connected to the negative pole of the battery. Can you see we need the supply of electrons to go here, and this electrode needs to be negative to attract the positive cations. Would cations be forced to go, would go easily to a positive electrode? Would something positive be attracted to another positive? No. Okay, so in the galvanic cell, which we did last week, it was the reduction potential that was driving it, so it was making it go there. So it was zinc giving off electrons easily because the copper was grabbing them. This is where we're trying to force the zinc to go and make it attractive. So this electrode must be negative to make the positive zinc ions be attracted to it, to make them move that way. And similarly, this electrode is positive. We connect it up to the positive electrode so that the electrons get attracted to move around and complete the circuit. So that's why there has to be that swap. If you made this cathode positive, you would find there'd be no reaction, that you wouldn't get the zinc plating on this electrode. It would actually, if you made that one positive, it would turn around and plate it on this one over here. Okay, so it would swap around. Now, a way to remember that negative and positive, this is in your booklet, but it's a way to remember a poem. So a negative cat became very fat, consuming cations for tea. So the cations are coming. And the cat's saying, it is as I feared, this diet is weird, as reduction is happening at me. Remember, reduction in the English language seems as though it's getting smaller, but of course, in the chemical sense, if cations are depositing on as metal, the electrode is going to get fatter because it's getting more and more atoms being added onto it. And then what's happening on the other side? An ox overheard and replied with these words, "I have the opposite problem, you see. I only get thinner with anions for dinner, no matter how positive I be." So it's to remind you that the anode is positive, because remember an-ox, the oxidation at the anode. So do you think you'd find that useful to remember that for electrolysis, the cathode is negative? It may be useful for you, and otherwise make it with drawings. Notice I've made this cat now look negative. The previous time you saw the cat, it had crosses for the eyes. Now I've made its whiskers and its mouth and its eyes all negative. So minus signs. Okay, now, so what I'm trying to show here is, remember these reduction potentials? In an electrolysis cell, the galvanic cell, you had the strongest reductant having to react with a stronger oxidant down here for the reaction to work. Okay, so you had a big person grabbing the electrons, so the stronger oxidant would grab the electrons from the weaker one. Now in the electrolysis reaction, because we're giving energy to it, so we're supplying the energy, it's as though, now just remember this one's got the red gloves, the big guy's got the red gloves and the green shorts. So when we supply energy, it does the opposite. So the red gloves one with the green shorts becomes smaller because we're now pushing it the other way. So it's, if you like, the energy from the electrons has made the little guy big, and you can now do the opposite. So that's a way to remember. We're forcing it. So before we had the letter C happening, now with the electrolysis, we can have something down here, like for instance peroxide. We can force it to go the other way and make, say, peroxide react with, say, tin ions to make tin being formed. Whereas in the past, that wouldn't work chemically. Does that make sense? So for electrochemical, we move downwards like this in a C. For electrolytic, we can move upwards like this. So as an example, I can make zinc go to zinc ions and make magnesium metal being formed if I supply the current. Yes, Andrew. So by giving it the energy, I can force the reaction to work. So let's look at a reaction that's happening here. This is now an electrolysis reaction, so I'll get it going while I talk. Electrolysis of water, the last experiment you do is done in by a slightly different method, but you're still breaking up water into two different gases, the oxygen. Now this is the negative electrode, that's the positive electrode. So I've tried to show here the positive electrode is always the bit that sticks out. With any battery, it's the bit that sticks out. So here they're breaking down the water, and which side is giving off more gas? The right-hand side or the left-hand side? Does anybody want to have a go? You can either look at the test tubes or you can look at the bubbles. The right-hand side. So that's actually because we're splitting water into oxygen and hydrogen. We're getting more hydrogen being formed because there's more hydrogen. There's 2 atoms of hydrogen to every 1 atom of oxygen. So if hydrogen is being formed, you could even try this at home, better perhaps than the one I've done with milk bottles and so on. If we have hydrogen being formed on the right-hand side, is that the anode or the cathode? Well, first of all, is it reduction or oxidation if hydrogen gas is being formed? So think of oxidation numbers. From what's the oxidation number of hydrogen in water compared to the oxidation number of hydrogen in hydrogen gas? Oh, I'm going to just stop it here because now they're doing another electrolysis thing. Okay, it's reduction. The hydrogen ions are gaining electrons to form hydrogen gas. And if I just go back a bit, let's go where it shows. I'll go a little bit more where you can see something. Oh, okay. I'm not, it was based like this. So if it's on the right-hand side, if reduction is happening, what anode, what, I'm trying to not give you the right answer, so I've given you a different answer. What electrode is on the right-hand side? We know it's the negative one, and we know its reduction is happening. So what is this, the cathode or the anode? It's the cathode, because reduction happens at the cathode, correct, and the cathode is negative. And oxygen, if you think of the oxygen, the oxidation number is changing from 2- for oxygen and water to 0 for oxygen gas. So it has lost electrons. So the oxidation is happening at the positive anode. Okay, right, Amy, I see is typing. So basically what we've got here is reduction. And remember our voltage, this was our reference one. We just arbitrarily gave it a value of 0, and we just compare everything with the hydrogen electrode. It's at standard conditions, of course, at 25 degrees C, 1 atmosphere pressure and 1 mole of hydrogen ions in solution per liter. And this is the other reaction. And of course, remember, we're driving the reaction the other way around, so water is going this way. So our products are from the water is oxygen, I've highlighted it in bold, and the one on the other side, which is the hydrogen gas. And what can you tell me if I was trying to work out my E cell value? Would it be positive or would it be negative? Remember, the E cell is when we say E cell is equal to the reduction potential of the reduction half reaction, subtract the reduction potential of the oxidation half reaction. Would anybody like to work it out? This is going to be the reduction, that's going to be the oxidation, because we're going as sort of a bottom round C. Anybody would like to have a go? Okay, I've swapped it around to make it clear that it's oxidation happening there. Okay, my reduction, remember, is my hydrogen, so I have to put the 0.00 in there, and my oxidation is the 1.23 volts. And do you see that for electrolysis reaction, it's always going to be negative. So the reaction is non-spontaneous. Correct, Andrew, or what you've got there? It's non-spontaneous. So we need the electricity, we need that energy to drive it, to make it work. Otherwise it won't happen. And as Andrew said, it is spontaneous in the reverse. If I took hydrogen gas and I took oxygen gas, if they're at the right ratio, and I added a spark to it, you'd get a very big explosion. That's what they use for rocket fuel, actually. They use solid oxygen gas, so you can see it's really super cooled, and hydrogen gas, and then they have a spark to it, and it's enough to send a rocket into space. Okay, so that is the spontaneous reaction. We're doing the non-spontaneous one here by supplying energy. Okay, now we also use electrolysis, not just to make things, as you saw there, we can make hydrogen gas and oxygen gas. We can also make other substances. So what we're doing in here is we're going to be making chlorine gas. So from copper chloride, we'll be making chlorine gas, and we'll make copper. You can see from this that sort of reddy brown of copper. So if you just watch this one, And again, they're showing you, can you see the bit that sticks out is the positive pole and the other one is the negative. Okay, there they're showing you it's positive, right? And that's the negative side. So work out which one is the cathode and which one's the anode. So remember, a negative cat became very fat. Okay, so this is the cathode. Can you see the blue color is fading because the copper is starting to deposit on there? So the blue copper ions are now disappearing because you're forming copper metal. And let's take that back a bit. And I'll just stop there. So the blue color is fading. This is all the things you need to explain. Remember that triangle I did of macro, the observations. You must make sure you give detailed observations. You've got to give the micro, so what's happening at particle level. The copper ions are depositing onto the copper or onto the cathode and gaining electrons to form copper metal. What's happening at the, and then the final thing is the model. So you give all your E-cell equations, your reduction half and oxidation half equations. So you must make sure you have all those three bits in it. What's happening at the anode? What do you notice up here? What do you observe? The bubbles. So if you're getting bubbles being formed, it means it must be a gas. And think about what sort of gas do you think you could get? The Cl, the chlorine gas, correct. Okay. Now, in the booklets, I've tried to go into quite some depth, more than what you actually need for the task. But because this is all in aqueous systems, remember the hydrogen gas could perhaps be formed at the cathode, or you could have oxygen gas being formed at the anode. So if the solution is too dilute, you could even get oxygen gas being formed. It just depends on the reduction potential of chlorine compared to oxygen. So there's always those competing reactions. So if you were to say doing this at home, it's not necessarily as straightforward as you might expect. You'd have to think of what else is present. So water is present, so that can also undergo electrolysis. Okay, so there you basically got it. You got your copper with a voltage, a reduction potential of 0.34, and your chlorine of 1.36. And remember, we're going the other way, so our copper ions are going to form copper, and your chloride ions are forming chlorine. So we're doing the opposite C. So our E cell value, okay, there's to show it's the oxidation. Can you see we get a negative value? Okay, now what I've shown in the next two things is just to show that it can be more complicated. So I'm saying this is for interest only, but I'm going to switch these on, and this one is quite a long one, so I'm going to move it on to 3.29. Whoops. So still catching up in this one. Just have a look to see what happens. So we've got tin chloride over here, and notice they've just got slightly different conditions. So have a look, you're getting the tin metal being formed. So remember, cations to cathode is, so this is going to be the cathode in each case, because the metal is being deposited there. But here, if there's hardly anything happening, but can you see there's a bit of a vapor coming off? I don't know if it's very clear from where you're at. So gas is coming off, even though you don't really see bubbles. Whereas here there is a solid being formed. I don't know if you can see, it's getting all white over there. He's just put a bit of extra metal in there. So you're going to be seeing it's acting a bit like its own electrode. So metal will form there, and that'll be the anode being made there. But it's very pretty, isn't it? I liked it for its prettiness. So what we've got is the tin ions forming tin metal. And in the top case, we've actually got the water being formed. If I just go back and okay. So there's a gas coming off, and that's the oxygen gas. Whereas down here, and I'll just stop it. And there's also competing reaction. The chloride could also form chlorine. So you could have a mixture of oxygen coming off here or chlorine gas, depending on the concentration. What we've got over here is the tin being formed. So we've got the same reaction at the cathode, but because the concentration is a bit different, so, that should have gone back up again, sorry. What we have here is the SN2 plus is not only being reduced to form tin, it's also being oxidized. What is the oxidation number of tin in SnCl4? Can you work it out? Does anybody want to have a go with oxidation numbers? It's +4, because remember the chloride is a simple ion, so it's -1, and there's 4 of them. So if this is -4 in total for the chloride, the tin has to be a +4. Now, tin being such a very positive ion is going to be insoluble. So the tin chloride that's being formed, or the SN4 plus ion that's being formed, is going to grab any chloride that's around and will precipitate out. Now, as I say, you don't have to know that, but I've just included this slide so you can see that electrolysis, and actually even making batteries, is quite a fine-tuned endeavor. You know, it's not just mixing two things together and passing a current through it and getting the product you want. So this is the important bit you have to know for the task. You need to be able to compare the two different types of cells. So on the left, we've got the electrochemical or the galvanic cell, and you'll notice the features. We've got a cathode and an anode. We always have to have those solid bits to it, no matter what cell you have. But you've got a salt bridge separating the two. It could be a piece of paper, so thin cardboard. You could do it at home and just put thin cardboard in between. It could be a glass tube. There's normally those curved tubes with cotton wool on the end, so that the liquid doesn't pour out very easily. So they've got to work its way through. And of course, we have some means of either measuring the potential difference, like a voltmeter, or we simply have, say, a light bulb over there showing that current is being produced. So remember, electrochemical cell produces a current, and we show that either with a voltmeter or a light bulb, or some sort of, it could be an ammeter as well, some sort of way of measuring that electricity is being produced. You've got always the cathode, reduction happening at the cathode, and so the electrons are going over here away from the anode that's giving away the electrons to the cathode, and the cathode is positive. So that's the main difference between the two in terms of cathode and anode. Can you spot the other differences? We've mentioned them in the very first slide. So there are two other obvious differences apart from the positive and the negative cathode and anode change. So Andrew, I think you mentioned one of them before. And so Amy and Michael, have a go, because giving an answer, then I can at least sort of respond. So is there anything different you see between those two? Because you would have to explain it in the task. Right, okay. Andrew, you'd say with the electrolytic, it is spontaneous in the reverse direction. Also, just simply state it's a non-spontaneous reaction, and therefore you need to supply the energy. But if you also just simply looked at the cell, there's an electrical supply, to, like a battery, to supply the energy. And of course, there's no salt bridge, as you pointed out before. And then, as Andrew, you pointed out, because it's non-spontaneous, you have to supply the energy, whereas in the electrochemical, energy is being produced. Is that fairly clear? Okay, I see Andrew's typing there. Okay, right. Okay, so it's quite an easy task because that's really the most important bits. So let's have a go answering this. So what we're doing is comparing this electrochemical cell and the electrolytic cell, and we've just got a whole lot of questions over here to see how they change. So the reaction type, is it spontaneous or non-spontaneous? So for the electrochemical, which one is it? Spontaneous or non-spontaneous? Spontaneous, right? Okay. And for the electrolytic, does anybody want to have a go? Non-spontaneous, correct, well done. For the E0 cell, is it positive or negative for the electrochemical? Positive, correct. And for the electrolytic, it's negative, well done. Okay, so energy, is energy being produced or supplied for the electrochemical? Produced, well done. Okay, you got it. And for the electrolytic? It has to be supplied, correct. Now these are all the points you have to say in the task. Okay, you're not going to get it at a table like this. It's a report, so you've got to write it out. But these are the points you've got to cover. The cathode, is it negative or positive in the electrochemical? It's positive, okay? And, oh, sorry, I clicked too fast. It's negative in the electrolytic. So remember that negative cat became very fat, consuming cations for tea. Okay, the anode, is it positive or negative in the electrochemical? It's negative, and in the electrolytic, it is positive, correct. Reduction, does it occur at the cathode or the anode? So let's have a go for the electrochemical. Is it the cathode or the anode for reduction? The cathode. And for the electrolytic? Okay, now be careful, because I said for each case, it will be always cations to cathode. So these first over here, few questions are where they're all different or opposite each other, but now we pretty much for the next two are going to get the same answer. So it's always cations to cathode, and so if it's cations to cathode, they're gaining electrons, so it's reduction. Okay, and remember that other thing is reduction, so the C is a cathode, so that happens for both. So oxidation occurs at the cathode or anode. In both cases, it's going to be the anode. So these two are the times when it's the same, all the others are when they're different. Okay, now notice Andrew's typing there. Yeah, okay. Okay, Andrew, you might have gone ahead with this. How would we know which is the anode in each cell without looking at the products? So we don't know if reduction or oxidation is happening. It's if we just went to the previous slide and we looked at those, how would I know where the oxidation or reduction, or which one's the anode? So I'm just going to go back. Go to slide. Oops. Oh, no, sorry. Previous, sorry, I've gone too much ahead. Sorry about this. I was trying to be, let's go the last, that one. Sorry. So how do I know which one's the anode in this case? Just if I just was given this, I couldn't see the products. Okay, I could look at my E cell value, and so if I know, say, one electrode was zinc and the other one was carbon, and so on. But otherwise, if you look at the battery of an electrolytic cell, how would I know which one is the anode? The anode has to be connected to which side of the battery? So thinking of these two different sides, the positive side. So if this was connected to the negative side, it wouldn't be the anode anymore, it would be the cathode. Okay, and then you'd have reduction happening here instead of oxidation. So whatever is connected to the positive side of the battery is the anode. And for the electrochemical cell, what happens here is that you'd have to look at the E cell value or the reduction potentials. So the cathode, remember, is the one, if reduction is happening at the cathode, then it's got to be the more positive value for the reduction potential. So that's what I mean by the last one. So if I just flick through very quickly, okay, the anode is a stronger reductant for electrochemical cell, and the anode is connected to the positive side of the battery in an electrolytic cell. Okay, do you think you'd be able to use all that in your report? So it's really in the level of detail. You've got to do all this detail. Okay, Michael, you'd be practicing as you go through the 3072. In fact, the booklet 3072 is actually a lot harder than the task. But as long as you get that idea of, I'm focusing on the important bits. So where will reduction and where will oxidation occur? Can you do those half equations? Can you do the full equation? Can you identify what's spontaneous and what's non-spontaneous, and where you need energy being supplied or energy being given off? So it's those sort of things. Okay, then you've got to do a bit about uses. And so the electrochemical cells, basically their use is really in a battery to supply energy. But that's really the only reason for electrochemical cells. So any battery you use in your cell phone and your laptop and your tablet, that's an electrochemical cell. And as I say, it's got quite advanced chemistry in it. If you went into that field, it's not just throwing two things together, because you've got to think of long life of the battery and so on and so forth. But lithium is the one that's used a lot because it's so high up in those reduction potential tables. So it gives a good voltage supply. Electrolytic cell has a lot of different uses. Has anybody been down to the Bluff, to that aluminium factory down in the Bluff, or near Invercargill? No, okay. I must admit I haven't been there either. But that is just an enormous electrochemical cell. Electrolytic cell. What they're trying to do is make aluminium by supplying it the aluminium cation with lots of electrons. That's why it needs so much energy. I mean, they've got their own little private supply of electricity from a dam there. It's because they've got to supply 3 electrons for every aluminium ion. So they need a lot of electricity to make one aluminium atom out of an aluminium ion. Compared to sodium metal, you only need 1 electron. With aluminium, you need 3. So it's very heavy on electric use. But that would be one thing where you refine substances, making aluminium. We've already said oxygen, gas, hydrogen gas. It's a way of doing that. Making copper, so refining copper out of a copper mixture, or refining silver out of a silver mixture. That's a very big use of it. Recharging batteries, of course, is where you just do the opposite to the battery. So every time you want to recharge a cell phone, you're supplying energy, so you're doing the reverse reaction, and you've turned your electrochemical cell into electrolytic cell. And then the last thing is when you plate substances. Has anybody got any, say, gold-plated watch or rings, or silver-plated or rhodium-plated or something like that? It doesn't have to be jewelry, anything that's plated, not that rich. Right, so really it's that plating is just done in an electrochemical cell, where you just put a thin layer of the metal you want on top of another metal. So as I say, rhodium, they do it over white gold, silver-plated stuff, gold-plated stuff. You wouldn't really necessarily plate iron on something, but you might plate, for instance, tin onto iron, so that the iron doesn't rust very easily. Or zinc onto iron. You know, when you've got galvanized zinc, it's a slightly different process, but it's the same sort of idea where you're putting zinc together with iron so that your iron doesn't rust. So let's have a look at some of those. So this is very quickly, you can see there, this is a brass key that is being plated. So brass is that yellow shiny stuff, and the copper is that reddish brown. And can you see what we've got here? A solution of blue copper sulfate. Now, your solution should always be the same iron or same element type as what you want to plate. So if you're trying to plate copper, should I have a silver solution? Iron, you just want the same iron happening. And if I carry on with this, then she'll take it out and you'll see that same sort of copper that's being formed. So there's the copper that's plated on. So that is the one use, the plating. Okay, here's another one where you're refining the silver. So, okay, it's basically saying these must a silver solution. So you've got to again minimize the silver solution. That little bag there is just to, if there's any dross, it doesn't contaminate your silver solution. So what you've got here is your bad silver in this one that you're connecting up, and there it's showing how it's being connected. And let's go back to this again. Okay, so what we're having, this is where the silver is depositing, so the silver goes to the cathode, so this is the anode. So they've got sort of bad silver here, and all the black stuff that's sort of dropping off is collected in that bag, and you've got pure silver being formed down there. So that's refining. And as I say, what solution should you use? So I'll actually stop that soon. You need a silver solution. And can it be an insoluble silver solution, or must it always be a soluble salt? Right, it has to be a soluble salt. So if you say using lead, don't say you're going to use lead sulfate as your solution, because it's not going to dissolve. Very little will dissolve. So a nitrate is normally always soluble, or an ethanoate. So those are always good options to use if you're trying to make a solution. So this has to be, as I say, your cathode, because your silver has to deposit on there, and your impure solid is the anode, because any silver coming off there that's on the impure will come and deposit on this side, and any dross, any other stuff will just collect in that little bag. So that's the refining part. Okay, so we've really looked at the making things. We haven't really done the rechargeable battery, but I think you've all had experience with that. And then we've looked at plating. Here is just for interest, because you might want to do it, is, has anybody ever taken apart a battery? Now, yes. So I suggest you, if you're going to try it, use the heavy-duty battery. Now it's German, but it's really a zinc carbon battery. So it's like a heavy-duty battery. Please don't do it like this person. Use gloves. It is acidic. Don't try and break up an alkaline battery. Do the acidic ones. It is acidic. It's not going to damage you. I mean, I've done it without gloves, but you'll notice there's a salt bridge. Can you see the salt bridge in there, that paper? That's all what you have to have for the paper. Let's sort of stop it so far. That is the zinc, which is going to be the anode, so that the zinc gets corroded. Okay. So eventually the zinc will get thinner and thinner and pitted and pitted. He's taking off the salt bridge at the moment there, the cardboard. And inside that is, can you see all that black stuff? That's basically manganese dioxide, a bit of ammonia, a bit of chlorine, a whole lot of different things. that manganese dioxide is actually the cathode, but in order to make electrons move through quickly and easily, that's a carbon rod. Because remember, graphite is a conductor of electricity, and let's just stop it there. So there's the zinc, there's the salt bridge, that's the electrode. Remember we said we could sometimes use platinum or carbon. That's just to make electrons move through there easily, and that actually is the manganese is where the reaction is happening and the electrons are being gained. So that was just sort for interest, if any of you want to try that. And finally, just the 3 different things you do need, if you want to do well in the task, you do need to handle all of these. So talk about your observations. Make sure you've given a description of every reactant and every product. The color, the state, is it a solid, is it aqueous, or what's happening. The microscopic, talk about the cations, or where are they migrating to the cathode, to the anode, and why, and so on, and what is happening, the reduction, the oxidation. So explain that in detail. And of course, always support your answers with the model or the symbols and the formulae and the equations. So your E-cell calculations, your balanced equations, your balanced half equations. And otherwise, that is it. So any questions? Not at the moment. Okay. Right. So we'll stop there. And next week we're going to start the first lesson on the external 3.4. So we'll be looking at 3041. Are you more or less all keeping on track, or are these lessons going faster than what you're keeping up with the booklets? Okay, they're good. Yeah, because I'm trying to sort of keep you on track. So if you were going to do all, you know, 6 standards, you'd be on track. And okay, Andrew, if we're going a bit faster, at least when you listen to this, when you do the booklets, you'll hopefully find it a bit easier. Okay, well, you're already way ahead of Junior anyway, because you're also doing it there. Okay, well, otherwise, we'll stop.